Come in this beautiful subject of thermodynamics, and I myself Shivam Dixit welcoming you all in this beautiful series for GATE 2027. Sujata Yadav Arsh, very good evening. Am I audible and visible to everyone? Am I audible and visible to everyone? Right, okay. So let's start. So basically in previous class, I think you know life love, very good evening. So in last class we have discussed about entropy and exergy part, right? So we have discussed the exergy part also, available energy, availability, irreversibility, second law, efficiency. So today we are going to talk about the the properties of pure substance, right? Today we are going to talk about the properties of pure substance. First of all, what is pure substance? So pure substance is the substance which have same chemical composition throughout, or homogeneous chemical composition throughout. That is basically called as what? That is called as a pure substance, like oxygen, nitrogen, right? And so carbon dioxide. So all these are basically what? These are basically the pure substance. For example, in one container, if you have oxygen, so everywhere if you see the chemical formula is going to be same, like O2, 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 right? Okay, not only this, the mixture of two pure substance can also be a pure substance. The best example is our air, right? The only thing is composition must be homogeneous. So whatever dry air present into the atmosphere, that is basically considered as a pure substance. It means that why it is considered as a pure substance. The reason is, see, we, as per the analysis perspective, we are considering the dry air as a combination of or mixture of oxygen and nitrogen, where by volume if you see, then 21% oxygen is there and 79% nitrogen is there, and this composition is actually same throughout, right? If you measure the chemical composition of air in my room, then you will find 79% nitrogen and 21% oxygen. Whereas if you measure this in your home, then also you will find the same. If you measure in the Delhi Jantar Mantar, then also you will get the same. If you measure it in a Patna, then also you will get the same 79%, 21%. If you measure in a Mumbai, Thane, Pune, I think Lucknow also, Jaipur, Patna, and there are Kolkata also. So if you check the chemical composition of the air in any of the city, any of the place, you will find approximately similar kind of composition, means 21% oxygen and 79% nitrogen. So I have taken this few of the name, right? I have taken few of the name, like Delhi Jantar Mantar, or it may be like Lucknow, or it may be Patna, it may be Jaipur, or maybe Kolkata, right? So there are multiple, Mumbai, Thane, Pune, right? So in these places, right, if you see the composition of air, right, the composition of air is basically 79% oxygen, 79% nitrogen and 21% oxygen. Why do you think that Delhi will have something different composition, right? CO2 is going to be more, okay? Heat is also more, right? Currently heat is also more because temperature is more, right? Okay, no problem. So what we are discussing? We are discussing about pure substance, right? So in this case, if you see that like I'm not talking about CO2 here, I'm only talking about like dry air which we are considering in our analysis, that is oxygen and nitrogen. But okay, but the wet air, or I would say moist air, you may heard about, right? The actual air present in my room, that is moist air. Means moist air is basically consist of dry air as well as water vapor. So water vapor composition may different in different places, correct? For example, see, that's what the reason that moist air is not considered as a pure substance. For example, if you look at the moisture content in Lucknow, that will be different from the Delhi, that will be different from the Chennai, that will be different from the Kerala, that will be different from the Mumbai, that will be different from the Kolkata. So everywhere the humidity is basically different. So the moist air is basically not considered as pure substance. Okay, so two things I have told up to now, P Madhavan, right? Two things I have told, that a substance which have homogeneous chemical composition throughout, that is called as pure substance. Example is nitrogen, oxygen and all those things. Even the mixture of two or more pure substance can also be treated as pure substance. The only thing is the chemical composition must be same. The third and most important for us, that is like there are some substance, right? If two or more phases of same substance are exist, please listen here carefully. If the two or more phases of same substances exist, in that particular case, under psychometry analysis we have studied. Okay, very good, perfect. So in our case, generally in this chapter we are going to talk about the properties of water. So why water is considered to be a pure substance? Water is a pure substance because the chemical composition is same everywhere, H2O, H2O, H2O. Not only this, even the mixture of water and steam is also considered as a pure substance. The reason is steam chemical composition is also H2O. Steam is also H2O, ice is also H2O, and water is also H2O. It is an invariable chemical composition irrespective of phase. In case of water, the chemical composition is not changing with respect to the change in the phase, right? So even if one or more than two or more than two phases are exist, right, in a container, and the chemical composition is same throughout, then also we'll consider it as a pure substance. And one more thing, air is a pure substance, but air is a pure substance only when it is in gaseous phase. Because I have seen that in some of the interview they used to ask that even if I condense the same like water, right? Water is going to be converted into steam, or steam is going to condense to the water, again water is converted to the ice. Then in all those cases, the pure, it is pure substance throughout, right? Because chemical composition is not going to change. But in case of air, it is not valid. Means for air, if you change the air, like liquefy the air, if you liquefy the air, then it may change, right? If you liquefy the air, then it may change. Okay, because air have several components. Even if I consider nitrogen and oxygen, then the condensation temperature of nitrogen and oxygen is different. So they are going to be condensed at different temperatures, and the liquid oxygen and liquid nitrogen may not mix homogeneously. Okay, so this is all about what? This is all about the pure substance. Now I am going to see one more thing I would like to share here before starting the topic. I would like to share here this application of thermodynamic series will also be there. It's not started yet, but it will start later. Don't worry about it. Okay. Now I'm going to share one very important information, that in this, the chapter name is properties of pure substance. If you look at here, the chapter name is properties of pure substance, but actually we are not going to talk about all the pure substances, because there are many pure substances, but basically we are only going to talk about the water here. We are only going to talk about the water. So basically the chapter name of this subtopic should be properties of water. Even some of the books, they are writing the chapter name as a properties of water. So if we are only going to study the properties of water, then why the chapter name is properties of pure substance? The reason is that most of the pure substances have similar kind of way of study, right? So if you learn how to find out the properties of water in different cases, right, with the help of steam table, then you can find out the the other pure substances properties similarly. Okay, that's why the chapter name is generic, right, properties of pure substance, but we are going to talk about water only here, right? We are only going to talk about water. Okay, so up to here I hope that everything is clear, right? Liquefy the air, as in O2 cylinder we compress it till it become liquid. Yes, true. Similarly, liquid nitrogen also I have heard that use some PhD studied. Yes, true. See, condensation, right? Please try to understand. Okay, the same point we are going to discuss actually, right? Whether it is a condensation or vaporization or freezing or melting, whatever phenomena it may be, these phenomena can be done by varying any of the property out of two properties, that is pressure and temperature. Please listen here carefully. Means, for example, if you have water, just listen here, right, carefully. Same logic is here also. Logic I'm telling you, you will be able to understand. Let's say you have a water. Now you want to convert this water into the steam. Then what you will do? Sir, I will heat it and increase the temperature and it will convert into the vapor. Yes, this is one method. There is one more method, right? You start decreasing the pressure. When you start decreasing the pressure, then also water will convert into the steam, right? Let's say you have a water and put into one container, right? Please listen here carefully. Put into one container and start reducing the pressure inside the container somehow. Start reducing the pressure in the container somehow and reduce the pressure like in range of partial pressure actually, reducing the saturation pressure. So if you go below saturation, I did not recall the exact value of that saturation pressure at particular temperature, that will be given in the steam table, right? So if you look at the steam table, let's say the temperature in your room is 30 degree. So at 30 degree the saturation pressure will be, let me check and tell you exact value. I'm telling you, I think you people have that steam table, right? I'll share you the steam table in your group. Just go into the group because today it will be required. So I'm sharing one information. I'm sharing one file to you guys. Where is that file? That is my problem. I need to search. Yeah, so I have shared. Just go and check in my Telegram channel. You will get the steam table. So in steam table, if you look at 30 degrees centigrade, page number 914. Let's say our temperature is 30 degrees, then saturation pressure is 4 point something degree, right? So please try to understand. Let's say you have water at 30 degrees centigrade atmospheric pressure. Now you want to convert into the steam, then you have two options, my dear student friends. First option, you just heat it at atmospheric pressure, and once it will reach to the saturation temperature, that is 100 degrees centigrade, then this water will convert into the steam. Another method is you just put into one container and close it and start reducing the pressure inside the container. If the pressure inside the container is going to be like less than, like nearby 4 kilopascal, if it will be nearby 4 kilopascal, then it will vaporize, then again it will vaporize. So if you want to convert water into the steam, then there are two methods: either you decrease the pressure or increase the temperature. You also have the same question, right? Now you just asking the reverse process, means you have like gaseous phase, you want to convert into liquid phase. So two options are there: either you decrease the temperature, here we are increasing temperature, so here you decrease the temperature, or another one is reduce the pressure. Generally we are doing the both, increase the pressure, right? Increase the pressure. So two options are there. So in the cylinder, actually we are filling the oxygen at very high pressure. Once you are putting into the high pressure, then as the pressure will increase, then at the given temperature itself it will convert into the liquid. That's why when you are seeing in LPG and all other things, oxygen cylinder or LPG cylinder or nitrogen cylinder, so everywhere it is actually liquid. If you see that liquid is there in the cylinder, but once you open it into the atmospheric pressure, then it will immediately convert into the gaseous phase. Okay, and that's all the reason. It will take the heat from the surrounding, right? It will take the heat from the surrounding. So that's what, whenever you are using, let's say, gas stove or LPG stove, then LPG cylinder will become cold, correct now? Okay, let's talk about the phase transformation of pure substance. So for example, I have, please listen here carefully, so I'm going to talk about the TS diagram. Okay, so initially I have water. Let's say here we have water at 1 atmospheric pressure and 30 degrees centigrade. So I have 30 degrees centigrade water, right? I have 30 degrees centigrade. So, why only we study about water and sodium chloride Cl is also a pure. See, the point is very much simple here, Lohit Lucky, right? Lohit Lucky is asking a very good question, right? So Lohit, there are a lot of things in this universe, in this world to study. There is lot of things that you can study in this universe, right? Number of things are there. You can study anything. Lot of things are there. Okay, I'm just asking one question: why you are studying thermodynamics, not the computer networks? Because thermodynamics is required. You are getting thermodynamics is useful for you. You are going to write the gate paper through mechanical paper. That's why you are studying thermodynamics, right? You are not studying computer networks. The reason is very, very simple, because you are not going to write the gate exam with a CS branch. Same logic here also. We are studying water because water is a very much useful substance for being a mechanical engineer. Very much helpful. All the steam power plants are there, nuclear power plants are there, right? Even for cooling purpose we are using everywhere, right? It's a lot of use. Water have a huge role in thermodynamics. Why? Because it have very huge amount of specific heat. C is equal to 4.18 kilojoule per kg Kelvin. So whenever it is used as a coolant, then it can absorb more amount of heat compared to the other substances, and it is a harmless also. It is available easily, correct na? Now I cannot say
cheap, right? Earlier I used to say that water is available free of cost, but nowadays water is very, very costly. Nowadays water is very, very costly, I'm telling you, right? I would not be get surprised. I will not get surprised if at right after 10-15 years, 10-15-20 years, we all have to buy the water to drink, I will not get surprised. Right? Okay. So water is very, very essential, not only for our life, it is for mechanical engineering also. So that's why we are studying, right? It is a very, very essential. You please try to understand, water is going to be a next gold mine in the world. We understand this. This is very, very important, right? So if someone is thinking of doing research, right, someone is wants to do the research in upcoming, like Sujay is here and some more people may there, then there could be, you can think of some alternate methods. If you invent any alternate method to convert any non normal water or sea water or river water, convert to the pure water which we can drink or which we can use in a data center or any other places. So that is going to be a revolutionary thing, right? So water is going to be a next gold. After 15-20 years, it is going to be a next gold. Next gold means the rate gold will grow, water will grow better rate, higher rate. Okay, let's talk about the pure substances here, right? So as I told you, I have 30 degrees centigrade water at atmospheric pressure. Now I am going to heat it. When you heat, then entropy will increase, because whenever you are adding heat in any substance, entropy increases and temperature will also increase, because we are supplying sensible heat, right? So it is increasing up to saturation temperature. Now once it will reach the 100 degrees centigrade, what is 100 degrees centigrade? That is called as saturation temperature. That is called as what? Saturation temperature. There is T saturation, right? Saturation temperature, right? Saturation temperature means the temperature at which the temperature at which phase change may take place. Okay, now so it is a sensible amount of heat. Now at 100 degrees centigrade, water will start converting into the steam, and it will take latent heat, right? So it will take latent heat, so there will be no any change in the temperature, because it is taking only latent heat. But we are supplying latent heat, we are supplying heat through any mode, entropy value will increase. Then it will reach the 100 degrees. So at point 2, what we have? At point 2, we have 100 degrees centigrade of water. At point 3, what we have? 100 degrees centigrade of steam. Now we are going to increase the temperature further, and it will become superheated. So this, and in this complete process, the pressure is going to be a constant, right? Pressure is basically constant. So this is a constant. So this is a constant pressure line in a TS diagram for phase change of a water in atmospheric pressure, right? Atmospheric pressure. Okay. Now what I'm going to do, I'm going to repeat this experiment. I'm going to repeat this experiment at high pressure. High pressure means let's say we have one pressure cooker. Now I'm heating the water, which is at 30 degrees centigrade initially, in a pressure cooker where pressure is more basically, and converting into the steam. In that case, what will happen? In that case, what will happen? See, when we are increasing the temperature, when we are increasing the pressure, then saturation temperature will increase. Saturation temperature will increase, right? So it is, let's say, 120 degrees centigrade, for example, right? And then it will take latent heat, but lower than normal pressure, lower than atmospheric pressure, and then it will go something like this. So here this P1 is going to be greater than PATM. What I'm trying to say, please listen here carefully. Right, two things your mother may have. If you ask your mother, then she may share you some very good information. The first information, in case, like, if you are taking one simple pot, right? Simple pot, and in that simple pot, if you are taking water which is open to the atmosphere and you are heating it, so the boiling will start at 100 degrees centigrade. And to convert water into the steam, very high amount of latent heat is required, 2256 kilojoule per kg. For 1 kg, if you want to vaporize the 1 kg of water at atmospheric pressure, then it will take 2256 kilojoule per kg of heat. But at the same time, if you ask your mother that if I use pressure cooker, then will the boiling will start early or later? First question. And will it take more amount of energy or less amount of energy? Then your mother will say, no, it is going to be a later, means the water will start boil at a higher temperature. If you increase the pressure, then water will start boil at a higher temperature, I mean, let's say 120 degrees centigrade. If you touch, right, boiling is suppose taking place in normal pot and in a pressure cooker. If you touch both, then you will feel that pressure cooker is basically a more hot, right? Temperature is basically more. Now the next very important point. The next important point is the latent heat of vaporization at high pressure will be less, right? Will be less, means less amount of energy is required, less amount of LPG is required. So your mother will say, oh, if I use this pressure cooker, then we can save some little bit LPG, because LPG is very costly nowadays, right? So that's why you can save the amount of LPG expenditure by using pressure cooker. Okay, fine, perfect. Okay, now come to the another interesting fact, that why boilers are maintained at very high pressure, right? This question is mostly asked in most of the interviews. Why boilers are maintained at high pressure? The one of the most important reason is, at high pressure the latent heat of vaporization is less. So if you are maintaining your boiler in a steam power plant at high pressure, then the requirement of latent heat is basically less. The requirement of latent heat is basically less. Okay. Now, if you go into the let's say mountains, right? So mountains actually pressure is less. So if pressure will be less, then water will start boil at a early, right, low temperature, right? It will start boil at a low temperature, let's say 50 degrees centigrade only, and it will take high amount of latent heat, and then it will go like this. So it is P2. So P2 is basically less than PATM. Now please try to understand. There is one very interesting questions, right? There is one very interesting question, Hemu, that is asked by most of the people sometime, that why it is difficult to make prepare food in mountains. Because in mountains, please try to understand, in the mountains the water will start boil at a very low pressure, let's say at 50 degrees centigrade only. In 50 degrees centigrade, it's very difficult to cook the food, right? To cook the food, a minimum certain temperature is required. If the temperature is lower than that, then it's very difficult to cook the food. So this is one of the important reason. Now some people will ask that, sir, this line seems like a straight line and this line seems like a curve. The reason is very simple, right? The reason is very simple. Whenever in any parameter, I'm telling you, it is okay. I can tell you one thing, that it is experimentally, first thing, right? It is actually experimentally. When it is a water, right, the temperature rises in the water as compared to the entropy, then it is a straight line variation. It is a almost straight line, almost, not exactly, but almost straight line variation. Correct? Na? It's almost a straight line variation. Whereas in case of here, it is basically diverging lines. It is basically a diverging. It is a practical diagram. It is a practical diagram. Okay. Even though anywhere, if straight lines are there, means if out of two parameters, one parameter changes small, then we can consider it as a linear variation in any of the property, not only here, anywhere, right? So here actually compared to the temperature change, temperature is changes in 70-80 degrees centigrade, but the entropy change will be comparatively lower, right? That's why compared to this region, the entropy change here is very small. That's why it seems like a straight line. Okay, no problem. Let me tell you one more interesting fact, that this here we have saturated liquid, here we have saturated liquid, here we have saturated. If I match all these lines, then it will be saturated liquid line, then it is called as saturated liquid line. If I match all these points, right, then here we have vapor, right, here we have vapor, so it is a saturated vapor line, right? And these curves are going to be matched at a certain point, right? This point is called as critical point. This point is called as critical point. So critical point is a point where saturated liquid line and saturated mountain कब जा सकते, अभी निकल लो। अच्छा चंदन सर, sorry, I thought of someone else is there, but dashing Chandan sir is here. So I would like to request all of my students to welcome Mr. Chandan sir. He is one of the most finest faculty as far as EC branch is concerned. And you know, I have very good relation with the EC guys. Even during my BTech time, there was one EC madam, right? I have shared that story with you also. So I would like to request to all my students to welcome Mr. Chandan Gupta sir, because he is from EC branch and he have secured AIR 4 in GATE exam and AIR 12 in ESE exam. So why no one is? Good evening Chandan sir. Okay. So if you want mechanical engineers, right, if you want any kind of help, not only from me, from Chandan sir, then you can tell me. I will give his contact number directly. You can talk to Chandan sir, no problem. And you know, Chandan sir have one very special quality which most of the electronics engineers have, that he did the love marriage, right? So if any mechanical engineer wants to know that what we need to do to get you know, a love marriage, then you can connect with the Chandan sir. Okay. Sir, I'm preparing for GATE 2027, so what should I do? Good evening bachcho. Okay, Chandan sir is still here. I thought he gone. So everyone, if you wants to know how to get married, love married, then connect with Chandan sir. Okay, let's talk about here. So basically I have told you that you know, this what we are discussing here. Okay, we are discussing about phase transformation of pure substance. So the point where saturated liquid line and saturated vapor line meets, right? I am connecting with the Chandan sir. Okay, I'll share you the contact number, right? So so basically the point where saturated liquid line and saturated vapor line meets, that point is basically called as critical point, right? And the critical point, at the critical point, the latent heat of vaporization value is 0, right? Latent heat of vaporization is 0, means what is exactly going to be happen? For example, you are going to heat the water at a critical point pressure, then it will be heated, but without taking any latent heat, it will flash to the vapor, right? It will flash to the vapor. There will be no time, within no time it will flash, right? So it will be, the curve will be go something like this. This is pre-critical. The value of critical pressure is approximately 220.7 bar, right? Something like that. And the temperature at this particular point is 374 degrees centigrade. That is critical temperature, 374 degrees centigrade.
Now if you look at this diagram closely, then you will find that here we have liquid, here we have a vapor, and here we have liquid plus vapor, right? So this region is called as a liquid region or subcooled region. That is also called as a subcooled region. So what is the condition behind this subcooled region? That if the temperature, the actual temperature of a substance is less than the saturation temperature at the given pressure, then it will be in a subcooled region, right? So for subcooled region, the temperature of the substance must be less than the saturation temperature at the given pressure. Okay, now coming to the point, like superheated region, right? Superheated region means if the temperature of a substance is more than the saturation temperature at the given pressure is then it will be a superheated region. And here actually two parameters are required. Here exactly two parameters are required to identify the state of the system. Means if you want to identify the liquid exactly at any of the diagram, then minimum two parameters are required, minimum two properties are required. Generally these properties are pressure and temperature. Similarly, if you talk about the vapor, then again two properties are required, that is pressure and temperature. And this you can conclude from the Gibbs phase rule also. P plus F is equal to C plus 2, because here a single substance system and a single phase system also. So that's why there is no problem at all. Two minimum properties are required, and that is pressure and temperature. Now we are going to talk about the liquid plus vapor region, that is also called as wet region. This region is called as what? Wet region, right? So in wet region, if you look at here carefully, the wet region, then in wet region again two properties are required. Please listen here carefully. In wet region again two properties are required. Sir, why here two properties are required? The reason is very much clear. Because you might have thinking that as per the Gibbs phase rule, the number of properties required to fix the state of the system, here only one property is required. But actually you are committing one mistake. In Gibbs phase rule, P plus F is equal to C plus 2. P plus F is equal to C plus 2. Let's say if this is a Gibbs phase rule, P plus F is equal to C plus 2. Now in wet region, how many phases are there? Two phases are there. Degree of freedom we need to calculate. Number of component is 1 and 2, right? So F value will come basically 1. So as per the Gibbs phase rule, to fix the state of a system in a two-phase system or wet region, basically only one property is required. But you are doing one mistake here. Right? You are doing one mistake here. What is that mistake? What do you mean by F here? F is a degree of freedom. Degree of freedom means the minimum number of independent properties required to fix the state of a system. Again listen here, the minimum number of independent properties required to fix the state of a system. So F is giving you the minimum number of independent properties. For example, somewhere you are getting degree of freedom values 2. It does not mean that you can identify the condition of the system by the two properties, right? It actually means that minimum two properties are required to fix the state. Maybe 3, maybe 4. You are getting my point, right? For example, if you apply the Gibbs phase rule in my body and you are getting F value as a 4. F value 4 does not mean that by 4 parameter you can fix my condition. No, it means that you cannot fix the state by 3 parameters. Minimum number of independent properties required to fix the state, that is basically degree of freedom. So anywhere, if degree of freedom is coming something like 2 or 3, let's say 2, it doesn't mean that by 2 properties you will be able to fix. Less than 2 property you can't fix. This is the actual meaning. Either 2 properties will be required or more than 2 properties required. So same thing is here that in this particular region, minimum number of property requirement is 1. Minimum number of property requirement is 1. But actually it will require more. Actually it will require 2. Actually it will require 2. Okay, fine. So what are those two properties? You cannot say pressure and temperature. Why? Because pressure and temperature are dependent properties during the phase change. Pressure and temperature is a dependent properties during the phase change. So we need to define one property to identify the condition of a system in a two-phase system, and that property is called as dryness fraction. That property is called as dryness fraction X, right? Dryness fraction X, right? So okay, various region I have already told you. So basically dryness fraction X. What is dryness fraction? Just a minute, please. Wait. Just a minute, please. Just a minute, please. It is something urgent, I think so. Okay, so now I'll define one term that is called as dryness fraction. So dryness fraction X is defined as like mass of vapor to the total mass of mixture, right? ml plus mv. So basically this is required. Now with the help of this, if I find out the any property, if I find out any property in wet region, right? If I find out any property in wet region, let's say a specific property, let's say a specific volume. A specific volume value will come Vf plus X times of Vg minus Vf. Or I can write H is equal to Hf plus X times of Hg minus Hf. Or I can write U is equal to Uf plus X times of Ug minus Uf. Or anything else, S is equal to Sf plus X times of Sg minus Sf. Correct? So basically let's say atmospheric pressure is given, right? So at this particular pressure, this value, the value of entropy at this saturated liquid point is called as Sf. This is basically Sf, this is basically Sg, right? Means Sf and Sg representing what? Sf and Sg is actually representing the entropy of the saturated liquid, and Sg represents entropy of a saturated gas, right? Okay, so these things are basically going to be required. Okay, Now properties at various point, right? That I already told you. Let's say if you want to find out enthalpy and entropy, right? So this, let's say this is a given pressure, right? It is a given pressure, P is given, and this is basically saturation temperature, right? If our point is somewhere here, then it is very easy to find out the property, right? Let's say you want to find out enthalpy. So enthalpy at one point will be how much? Enthalpy at one point is equal, see, at this particular point enthalpy is known to us with the help of steam table. Let's say this is HF, this value is Hg, this value is Hg, right? So H1 value will come HF plus X times of Hg minus Hf. At the same point, if I calculate entropy, then it will come Sf plus X times of Sg minus Sf. Sg minus Sf, right? Now, if I take our point, let's say somewhere here, right? Our second point is, let's say somewhere here in this region, right? So here H2 value will come how much? H2 value will come H superheated with the help of steam, H superheated at P and T superheat, T sup. This temperature, let's say T sup. This temperature is T sup, right? So you can find like this. Another method is that you can find out like this. This is, let's say, the DH we can consider. So this value will come Hg plus Cp of vapor, Cp of vapor, T sup minus T sat, T sup minus T sat. But this formula, this below one, this formula only you have to use, if the direct value is not given, or if the steam table value is not given. 99% chances is steam table value will be given to you, right? Okay, now similarly, let's say our point is somewhere, okay, here entropy, if I calculate, S2 value will come as superheat at P and T superheat, and this can also write as a pressure is constant, so Sf plus Cp of vapor ln T sub by T sat. That we have already derived during the class. If you recall, we have already derived all this formula during the class. Now coming to the point like 3, right? Coming to the point like 3. So H3 value will come how much? H3 value will come HF minus C of water, T saturation minus T sub. This is T sub. And if I calculate S3 value, then it will come as SF minus C of water ln T saturation minus T sub. Like that you can get. So at any point you can find out the enthalpy and entropy. Okay. Okay, now we'll solve few problem based on this, right? Now we'll find out is we'll solve some problem based on this. So please try to solve this. Please try to solve this. Please solve this. Sure, sure, sure. You just ask me. You just ask me in a telegram. You just ask me in telegram. I will surely provide. I will provide you for sure. An insulated rigid container is divided into two parts by the thin partition. Okay, the one part of the container contains 6 kg of saturated liquid vapor mixture with the dryness fraction. So in one side of the container we have 6 kg of saturated mixture, x values given, right, at 0.3 megapascal. Okay, the other part we have 12 kg of saturated liquid vapor mixture, 0.6 megapascal of the same substance. No, okay, saturated at 0.6 megapascal. Okay, saturated liquid, sorry, it is a saturated liquid is there. Okay, saturated liquid, same substance. When the partition is removed, the system attains the equilibrium, the final specific volume of the mixture. So specific volume of the mixture you need to find out. So first you find out what is the total volume initially, right? What is the total? Very good, right? So here the data is also given. Very good, Madhavan. Data is also given here, right? So what is the like initial volume, initial specific volume, or I can say total volume initially? What is total volume? Mass into specific volume, right, in first container. So first container I am representing with 1, sorry, not first container, half part of the container, right, first part of the container, V1. So M value is basically 6 into this value will come VF. VF means 0.001073 VF plus X times of, what is X points? X times of VG minus VF, right? 0.60582 minus 0.001073, right? So what is the total volume? What is the total volume in one side of the container? Total volume in one side of the container, right? No, only one side of the container I'm talking about first. So 0.60582 minus 0.001073 into 0.7 plus 0.0010. So this value will come 2.5463754. Okay. Now here at 0.6 megapascal VF value is given, right? VF value is given. So basically what we have saturated liquid only, means VF only, right? So V2 value will be M2 into VF. So this value will come 12 into 0.0. So this value will come 12 into 0.001101, right? So 0.001101, okay, into 12, right? So this value will come 0.013212. This is meter cube, this is meter cube. So what is total volume? Total volume is V1 plus V2 after like if we remove the partition. So V1 plus V2 will come point plus 2.5463755. So this value will come 2.559587, right? Now we have to find out specific volume. Specific volume means total volume by total mass. So total volume is 2.559587, and total volume is how, total mass is how much? 12 kg. This one 6 kg means 18 kg, right? Divided by 18. So this value divided by 18. So this value will come 0.1422.
kilojoule meter cube per kg. Yes, correct.
Clear? Let's solve one more problem here. So this is one another problem. A pressure cooker contains saturated water vapor mixture at 100 degrees centigrade with volume of vapor being 8 times that the volume of the liquid. Means, please try to understand the volume. Means volume of vapor. Volume of vapor is 8 times the volume of liquid. Okay. Pressure cooker saturated water vapor mixture at 100 degrees centigrade. At 100 degrees centigrade. Okay. The volume the specific volume of saturated liquid and saturated vapor 100 degrees centigrade is given. Okay. So the quality of the mixture X value you need to find out. Please try to solve this. Please try to solve the X value you need to find out. But please remember, X is not defined in terms of volume. It is defined in terms of mass basically, right? It is defined in terms of mass. Please solve, everyone. So total volume of the vapor is equal to 8 times of total volume of the liquid. Now total volume of the vapor can be written as mass of vapor and specific volume of the vapor is equal to 8 times of mass of liquid, specific volume of the liquid, right? Now we'll take this side, so its value will come mv by ml. mv by ml value will come how much? 8 times of vl by vv. So VL is nothing but what? VL is nothing but VF, and this is nothing but VG. So 8 into 0.001044 divided by 1.6729. So this value will come. Yeah, please solve. Okay. I will wait. This value will come 0.0005 0.0049, something like that. 0.0049. Right. Now we have to find out X. X is equal to mv by ml plus mv, right? So divide with the ml, right? This value will come mv by ml divided by 1 plus mv by ml. It is 0.005 approximately, right? So this value will come 0.005 divided by 1 plus 0.005. So it will come approximately 0.005. Perfect, Sujay. Perfect. Perfect. Okay, next problem. Oh, it's over. So if you someone was asking about the some of the questions, right? So you can ask me for the questions. Where you need to ask, you can ask me if you need questions, right? For practice purpose, then you can ask me here, right? So this is my Telegram channel, Shivam Sir Physics Wallah. Right, Shivam sir, even students have, right? Students already have the practice sheet. Thermal set 1, I have all thermal set 1 and set 2 I have already given to the students, right? So if you want, even in this group, you just join this group and ask to the student. They will even provide you, otherwise I will provide you. Okay, so in this group you will find the questions, no problem. Okay, so this is for all about today's class. So this is all about today's class. So we'll meet tomorrow for the last topic, thermodynamic relation. Okay, so tomorrow again last class is there, and where we will discuss about the thermodynamic relations, and from Monday onwards a new subject will start. From Monday onwards a new subject will start. Okay, so thank you, bye bye, good night.